Hi, this lesson is about kinetic theory. Let's talk about the concept of pressure for gases and the kinetic theory and solve an example problem. So we know that pressure is the force divided by area. But when we think about gases in a room, for example, it's hard to think pressure as this force divided by area. So we can think pressure for gases as the resultant energy of the collisions between the gas molecules inside a room, for example. Okay, and we have from these collisions between the gas molecules, we can find this relation here, that the pressure times the volume equals 1/3 of the number of molecules times the mass of these molecules times the average speed squared. Okay? So what does this relation tells us? Let's take a look here in the formula. So if we have a fixed volume and a fixed mass, okay, we're dealing with the same molecules here. So if we increase the number of molecules for a fixed volume, we're also increasing the pressure of the system. Another thing is that, well, now for a fixed number of molecules of the same mass, if we decrease the volume, we're actually increasing the pressure of the system. And also, if for a fixed volume and number of molecules, if we increase the mass of these molecules, we're also increasing the pressure. For example, the molecular mass of the oxygen is higher than the nitrogen. So in a system with the same volume, the same number of molecules, the system with oxygen will have a higher pressure than the system with nitrogen. Okay, let's talk about the kinetic theory now. First, let's remember the ideal gas formula. So the ideal gas formula tells us that the pressure times the volume equals the number of molecules times the Boltzmann constant times the absolute temperature. Okay? Just remember, in this case here, this formula in this format is the number of molecules and the Boltzmann constant. Okay? Sometimes you can see as the number of moles times the gas constant. Okay, but let's work with this format here. Now we can just associate the ideal gas formula with the relation we've just seen before. So we have, putting these two equations together, this new one. We can just see that we can cut out the number of molecules from here, right? And we can rearrange the equation a little bit. We can multiply it by 3 on both sides. Sorry, on both sides, and divide it by 2, and we reach this equation here. But if you remember the left hand side here of the equation, this is actually the kinetic energy. We have half of mass times v squared. And now we are relating pressure and volume with the temperature. We're actually relating the kinetic energy of a gas system with temperature. So this equation here tells us that if we increase the temperature, we're also increasing the pressure of the system. Let's put now this in practice. So we want to calculate the average kinetic energy of a gas molecule at 20 degrees Celsius, and also to find the speed of a nitrogen molecule at this temperature. Okay, remember this is the Boltzmann constant, okay? So we can just use the formula, the relation we've just learned. So for the kinetic energy, we can calculate this average kinetic energy just knowing the temperature. So we can add the values now. Remember, it's the absolute temperature, so it needs to be in Kelvin here. And we have that the average kinetic energy for this gas molecule is 6.07 times 10 to the negative 21 joules. Now to find the speed of the nitrogen molecule, we can use the same formula. We already know the kinetic energy, alright? And we can add to the kinetic energy formula. Before this, we have to find the mass of the nitrogen molecule. So we have 2 molecules times the molecular weight, molecular mass, divided by the number of moles. We have a 4.65 times 10 to the negative 26 kilograms of nitrogen. Alright? Adding the values here and isolating the velocity, we have an average speed of approximately 511 meters per second. Okay, now it's your turn to put in practice what you've learned. So suppose that the average velocity of carbon dioxide molecules, I'm providing you the molecular mass here, in a flame is found to be 1.05 times 10 to the 5th meters per second. So what temperature does this represent? So you have here the average velocity, right? The molecular weight. Try to use the relations I showed you here today to find the temperature, okay? So write your answers in the comment sections and see you later.
What did you think about this video? We appreciate your feedback, so tell us in the comment section.